This is 3.2. This is part 3 of 3 videos, and it's talking about functions and polynomials and the graphs of those polynomial functions. So this is part 3. So if you haven't seen part 2 and part 1, go watch those parts first. So this is the ending part. So let's look at an example. So if I said graph this polynomial, notice this is a quite big polynomial. If I multiplied all this out, which I'm not going to, but notice this is x to the 4th, and this is x minus 2, x minus 2, x minus 2, because it's to the 3rd power. And then this is x plus 1 squared, so x plus 1 and x plus 1. So if I wanted to multiply all those out, I would get a quite big polynomial. And notice I'm going to end up getting x to the 9th power as my leading coefficient, and there's a 1 in front of it. So 1x to the 9th power. And so this is going to be an odd function, which again, if you notice back to video 1 and video 2, that means if I know it's x to the 9th, which is an odd function, I know the end behaviors will look like this. And again, it will do a lot of stuff in between, but I know automatically the end behavior is going to look like that. The other thing, go back to video 2 and notice the method of graphing is we want to find the zeros. So if we found the zeros, like we set this equal to 0, we know 0, 0. We know if we set this equal to 0, we know 2, 0. And we set this equal to 0, we know -1, 0. So those are automatic zeros. And notice, if we go back to the last time, plugging in intervals in between there, so, and we know the end behaviors, by the way, so the end behaviors are going to go like this, and it's going to go like this. And all we have to do is plug in numbers in between that. But I want you to notice this has the 0 has a multiplicity, this right here, the 0, 0, okay, so this is this guy right here. It has multiplicity of 4. So in other words, it sort of repeats itself 4 times. So if we literally wrote that 4 times, so that, instead of all equal to 0, we're going to get it repeating a multiplicity of 4. And so notice this 2, the 0 of 2. So 2 is a 0, but notice it has multiplicity of 3 because it happens 3 times. That's literally why I wrote it out 3 times. So you'll see that it has the multiplicity of 3. And the same thing with -1. -1 is the 0, and this has multiplicity of 2. So I do want to point that out to you. So notice I have an interesting comment here that you need to pay attention to. So it says the 0, 2 has an odd multiplicity. So notice this 0 right here has an odd multiplicity. So the graph crosses the x-axis at the x-intercept 2. So notice this guy right here, let me highlight it. So it crosses the x-intercept at 2, but the 0, 0, and -1. So these two zeros, those two zeros, notice it has an even multiplicity, So these have even multiplicity. This has odd multiplicity. And the reason why that's important, because if it has even multiplicity, so the graph does not cross the x-axis at those points. So notice, and that's something interesting to notice. So at those two zeros, it doesn't change the y value. So which is interesting because a lot of times students will just say, oh, here it's below. And I'm going to do this wrong on purpose, by the way. So a lot of students will just go above and then they'll go down and they'll connect because they think it goes above and then below, above and below. But that's not true. So if you notice on the even multiplicities, notice what's happening. It does not cross the x line. So it literally, here it does, in between -1 and 0, again, -1 is an even multiplicity, so it does not change the value of it, so the y value. So it actually goes below it. So it comes up and comes back down. And notice the same thing at 0. Again, this is also an even multiplicity. So it does not change the value, so it goes back down again. So what we need to really find is the number in between here at 1. So if we plug the number 1 in, we're going to end up getting -4. So then it's going to literally come back down here at -4 and then come back up. So everything literally, so it's going to look like this. It's going to come back down, but this is a 0. It's going to come back down. This is a 0. And it's going to go back up. So it's nice and smooth. I'm doing this in small transitions, so it looks like it's like a crisp sharp right there, but it's a nice smooth transition. All polynomials are smooth, and it's continuous and smooth. So notice it actually only goes above the y line right here. That's the only positive numbers. So as x goes towards infinity, so again, x, 6, 7, 8, 9, 10, 11, 12, as x goes toward infinity, y goes towards a positive infinity. As x goes towards negative infinity, -5, -6, -7, -8, then y goes toward negative infinity. So those are my end behaviors, but notice what's happening in between. Because of the multiplicities being even or odd, then you can figure out what if it actually changes signs or not to be able to do that. So that's an interesting concept, because you can sit here and make up something if it has even multiplicity. So even if it has even multiplicity, so you can even make up something like, let me go to graph paper here. So even if I made up some function that has all even multiplicity, so something like this. So, I mean, you can see the zeros, x equals 4, x equals 1, and x equals -2. So at -2, at 4, and at 1, but because they're all even multiplicity, so in other words, notice they're all even multiplicity, so they don't change whatsoever, and notice they don't change from positive to negative y values because of that. And notice this is going to be x to the 12th power. So if you did multiply all that out, it would be x to the 12th power. And that means the end behaviors are both going to look like this. And what's it going to do in between that? Well, I know that it's not going to go below it. Again, it's not going to change because of the even multiplicity. So it's literally going to go back up here. And again, you can plug in a number like 0 or something like that, but it's going to go up and come back down. And again, it's not going to go below it, so it's going to come back up again. So it might look something like that. Again, you'd have to plug in like x equals 2, x equals 3, x equals 0, x equals -1 to see how high that function actually gets. But I want to point out to you, because it's even multiplicity, it does not change the values. So if I did change the y value, so if I did change that to an odd multiplicity at 1, then it would end up going down at x equals 1. So just so you know, that's how you would the odd and even multiplicity relate. And then we've already talked about local minimums and local maximums, and that's just a review. This would be the local maximum, and this would be the local minimum of a point. But something a brand new word definition is local extrema. So it's basically the extreme of that point. So here in this scenario, in this graph, there are two local extremas. Again, that's the maximum and minimums put together. That's really what it's talking about. So here's the general format. So here's a certain polynomial. Then the graph has at most n minus 1. So for instance, whatever the n is, so y equals x squared, so this would have one local extrema. So whatever the highest degree is, you're going to subtract 1 from that, and that's at most it would have is one local extrema. So the parabola, basically what you normally have for a parabola, there's only one minimum there. There's only one minimum. There are no maximums on that, local maximums. And so that's really what we're talking about. Even on an x cubed, like this is an x cubed function, So notice exponent is 3, so 3 minus 1 is 2. So notice we have a minimum, we have a maximum, and that, there's 2 local extrema on that. So even if I had illustrations and simply ask you, how many local extremas, all you have to do, we're not graphing the entire function, but if you look at x to the 4th, notice 4 minus 1 would be 3, so this would have 3 local extrema. Again, I'm not asking which ones are maximum minimums. We can graph it and find out, but that's not my emphasis here. So this is x to the 5th, so I know that there are going to be 4 terms in that x to the 5th. Again, you should know what the end behaviors are. X to the 5th is going to look like that. It's positive, so x to the 5th is going to look like that. And there are 4 local extremas in between those 2 points, those 2 end behaviors. So that's why we're looking at this. So this is to the 4th power, so there's going to be 3 local extremas in it. And again, look, notice the 4th power positive. So I know that the end behaviors will look like that. So what happens in between that, I know that it's going to turn at least 3 times. And notice it would look like there, there, and there. Something like that. So, if we graphed it, we can find the local minimum, local maximum, but we just really want to find the local extrema right here, the number of them, and that's what that little rule says.